I guess, a kind of a silver lining to these virtual colloquia that we've seemed to have had some really pretty good attendance. And I think, there's obviously no limit on the number of people that can show up. That said, I wish we were doing this in person. I think Anne's going to be my 4th PhD defending virtually, and I really can't wait till we can get back and celebrate these, I think, the research of our great graduate students in person. But anyway, things as they are. It's my pleasure to introduce today Anne Sledd. Anne's been with my group for about 5 years now, or getting close to 5 years. She did her bachelor's in physics at Carleton College, graduating in 2014, and then went on to do a applied physics master's degree at University of Oregon in 2015, where, just looking at her CV, she actually is part of a patent on something called the matrix multisensor array. So I think I just learned something new about her that I didn't know in the 5 years that she's been working with me. So as I said, she's been in my group now for about 5 years. She began her research working on a data set that was fairly new at the time. It was created under the CloudSat project to basically gather together model and observational data sets over the Arctic region. And that drove her down the path of a lot of the research I think you're going to see today, at exploring basically the role of clouds in modulating Arctic amplification. One of the key results she came up with very early on in her PhD was that clouds have probably significantly masked a big portion of Arctic amplification due to sea ice loss. I think she's going to share some of that work with you today. And then that work led her to investigate even more what the role of clouds are on the time to emergence of polar climate change, and also how that's represented in climate models and reanalyses. And I'm also sort of happy to announce that Anne's already found herself a postdoc continuing Arctic research, but now using in situ observations and regional models. So she's going to be going to Boulder sometime in the summer to continue this work, working on the Mosaic field campaign. So without taking up any more of Anne's time, I think I'll hand it off to Anne, and we'll learn a little bit more about the role clouds are playing in the Arctic climate change.
Thank you, Tristan, for that very kind introduction. And is everyone able to see my screen now?
Yeah.
Okay, perfect. So as Tristan alluded to, today I will be sharing my research investigating the influence of clouds on solar radiation in the new Arctic with perspectives from observations and models. So as I'm sure most of you are probably aware of by now, the Arctic has been rapidly changing. So we've observed about 2 degrees Celsius of warming over the Arctic, which is about twice as large as the warming that we've been observing globally. With a warmer Arctic, we also have a loss of snow cover, both in terms of extent as well as mass on land. And of course, one of the most salient examples of climate change in the Arctic has been the loss of sea ice. And sea ice is important for the Arctic climate system. It regulates the exchange of moisture and heat fluxes between the ocean and the atmosphere. And the Arctic used to be characterized by thick multi-year sea ice that persisted throughout the melt season, whereas these days we see less sea ice that's younger and thinner and is melting sooner in the summer. And we can see on the bottom left in the figure of Arctic sea ice extent standardized anomalies that this loss of sea ice has been particularly great in the last few decades. And it's telling that since the start of the satellite era in 1979, the lowest 14 September sea ice minima have all occurred within the last 14 years. And when we're interested in Arctic climate change, it's natural to wonder how the Arctic will continue changing into the future. And to look at that, our key tool is to use global climate models. So here are figures using ensembles from the latest generation of the Climate Model Intercomparison Project, CMIP-6. On the left, we have average surface air temperature, and the ensemble mean is the thicker line in the middle, with ensemble members at the high and low end in the thinner lines, with gray for the historical record and different future scenarios in the different colors. And we can see that all models predict that the Arctic will continue warming regardless of what the future holds for greenhouse gas emissions. But the magnitude of that warming can vary pretty considerably depending on what model you look at. That spread is even more pronounced in September sea ice extent. And so while all models lose sea ice in the future, we predict, in one model, we might see a sea ice-free September in the next few decades, or sea ice might persist to the end of the 21st century. And so those would be two very different Arctic climates of the future. In both observations and climate models, we know that one of the main drivers of climate change in the Arctic is the ice albedo feedback. And sea ice has a pretty high albedo. It's quite reflective of incoming shortwave. And if we lose sea ice, if we have a negative anomaly, then more shortwave will be absorbed at the surface, which then leads to less sea ice and more shortwave absorption, and it continues the cycle in our classic positive feedback. However, those changes were all at the surface of surface air temperature and sea ice and snow loss. And when we use satellite imagery to look at the Arctic, the picture we see is a little bit different, and you might say the picture is a bit cloudier. And that's because the Arctic is a pretty cloudy place. So monthly average cloud fraction is generally at or above 60% throughout the year. And in these daily images for one summer in 2013, the Greenland ice sheet sticks out as being highly reflective. And around the image, you can pick out land. And in the center, we have sea ice with the Arctic Ocean basin and open ocean somewhere around the edge. And while sea ice is changing day to day in each image, those changes are harder to pick out because clouds are obscuring the surface. And clouds are quite important to the Arctic energy balance. So we think of clouds as having a warming effect when they increase downwelling long wave radiation at the surface, or we consider them as having a cooling effect when they decrease the shortwave that reaches the surface. And given, I think my title gave it away, that in this talk, I'll be focusing on how clouds impact shortwave radiation in the Arctic. And returning back to climate models for one more slide, since Arctic clouds are important for the Arctic climate, we also want to know how well climate models represent them. And in figure on the left, in CMIP-6, we have average annual cycles of cloud fraction, again, from the CMIP-6 ensemble. And we see that they models vary quite a bit in the magnitude of how much cloud cover they simulate, as well as the seasonal cycles and how clouds are changing from one month to the next. And different modeled cloud properties are one main reason that clouds have different annual cycles of cloud radiative effects, or CRE, shown here on the right. And in particular, I'll point out this large spread in shortwave CRE across CMIP-6 that leads to uncertainty over the summer of even the net effect of clouds, whether they're warming or cooling the surface. And so in the rest of my talk, I will be focusing on how clouds have modified net solar energy over the Arctic in the last few decades that have seen some dramatic changes. First, I'll be focusing on the contribution of clouds to the planetary albedo and shortwave reflection. I'll then move on to discuss clouds' impact on shortwave absorption and how that has been changing in recent decades. Throughout this talk, I'll be using the observational results to benchmark climate models in how well they portray the impacts of clouds on shortwave radiation in the Arctic. And so, as Tristan actually mentioned in his introduction, the observations I'm using come from Auroras, which is a collection of observations and reanalyses. And each dataset in Auroras has been interpolated onto a common grid with 2.5 by 2.5 degree grid boxes. And if the dataset was not already monthly averages, those values are averaged to monthly timescales. And so the specific observations I'm using are sea ice concentration and snow cover fraction from NSIDC EASE weekly products that are measured from satellites with passive microwave sensors. For shortwave fluxes, I'm using series EBAF, both all sky fluxes and a relatively new clear sky product. So these total region clear sky fluxes were created by the series science team to allow a more apples to apples comparison between satellite clear sky fluxes that are measured for scenes that don't have any clouds present, as compared to clear sky fluxes for models that are typically calculated by rerunning radiative transfer code after removing clouds from the atmospheric column. And so the series total region clear sky fluxes include adjustment factors that have been applied to existing clear sky broadband radiative fluxes that make the observed and simulated clear sky flux definitions more consistent. And I won't be going into any details of that, but I recommend people who are interested to check out the paper by Loeb et al. 2020. And as mentioned, I will be comparing these observations to CMIP6, both historical forcing over the 20th century up to 2014, as well as two future scenarios for the remaining of the 21st century. So first, we're going to ask how clouds impact the shortwave reflection over the Arctic. And in this first section of research, we are using a physical definition of the Arctic based on annual average 2-meter temperatures from the air sounder. And so the region that we are considering the Arctic is shown here on the right. And the main impact of this definition is that it removes the warm Atlantic waters that are generally ice-free throughout the year. To look at the influence of clouds over different surface types, we further break down the Arctic and use categories for snow cover over land and sea ice over ocean. And so this is not taking into account snow cover on sea ice. But for grid cells that are considered land, we, for each grid cell in each month, we put it into one of 3 categories based on the snow cover fraction. And we use the same limits to categorize ocean grid cells based on their sea ice concentration. And on the right, we have the annual cycles of average fractional area that each one of these different surfaces accounts for in the Arctic. And what we can see is that there's pretty strong seasonal cycles, that there's extensive sea ice and snow cover in winter and spring, and that they decline in summer, snow reaches its minimum in July and August, and September is when we see the sea ice at its lowest. So to quantify the role and contribution of clouds to the planetary or top of atmosphere albedo, we are using a framework from Donahoe and Battisti. And in this framework, we assume a single layer atmosphere that can absorb or reflect shortwave radiation, as well as a surface that reflects shortwave radiation, and possible multiple reflections between the surface and the atmosphere. And each of these processes is considered to be isotropic. And so based on this framework, we can calculate the surface albedo and the planetary albedo. And we can further consider the planetary albedo as a contribution from the atmosphere and the surface. And so this atmospheric contribution is really dominated by clouds and represents the direct reflectance by the atmosphere for shortwave out of space. And these albedos and TOA albedo contributions can all be calculated using gridded shortwave fluxes. which we have here with monthly averages from series EBAF over 2002 through 2012. So beginning with the surface albedo in March, we see that the surface albedo is quite high. We have extensive sea ice and snow cover. Throughout the summer, as sea ice and snow cover melt, the surface albedo lowers. And by September, we can pretty clearly pick out the Greenland ice sheet with its bright reflective snow and where there's still sea ice. And those albedos are much higher than open ocean or bare land. However, at the top of the atmosphere, things aren't changing quite as much. So the difference in the TOA albedo from March to September is not as great as the difference we see in the surface albedo, as well as within a given month. So September, the contrast between areas where there is the Greenland ice sheet or there's sea ice, the difference in albedo between those surfaces and open ocean is also reduced. And that's because the actual magnitude of what the surface contributes to the planetary albedo is pretty small, relatively speaking. And so remember that the TOA albedo is the sum of the surface contribution and the atmospheric contribution. And so like the surface albedo, the surface contribution is also at its highest in spring, and it declines throughout the summer. However, by September, over most of the Arctic, the surface is contributing near zero to the planetary albedo. And it's really only the Greenland ice sheet that sticks out as being reflected enough to contribute significantly to the planetary albedo. And so it's really the atmosphere and clouds that are providing the bulk of the planetary albedo, despite the highly reflective surfaces that we think of as typical for the Arctic. We can see this again in looking at the annual albedos. So here we have monthly averages for March through September, which are the months that account for over 95% of incoming shortwave into the Arctic. And so in each of these figures, we have albedos averaged over the full Arctic in black, as well as averaged over the different surface types I discussed earlier based on the amount of sea ice or snow cover. And so beginning with the surface albedo, over the full Arctic, we can see again a strong seasonal cycle. The surface albedo over the full Arctic decreases by about half from spring to the end of summer. We can also see that surfaces without any snow or sea ice have very low surface albedos and much lower than areas that have some or all sea ice or snow cover, which are some of the most reflective surfaces in the Arctic. But again, when we compare those strong differences that we can tell at the surface to what we would see looking at the top of the atmosphere, there's a damping effect. So the planetary albedo does not change as much throughout the year as the surface albedo. It doesn't have that strong halving that we saw at the surface. And when we compare different surface types, they also don't vary as much. So this blue line is open ocean, and it's not as different as grid cells with all snow or all sea ice, like what we see of their actual surface albedos. And again, that's because on average, the surface is not contributing that much to the planetary albedo. So averaged over the full Arctic, again, this solid black line, the surface contribution peaks in April at about 0.2. And when it's at its greatest, the atmosphere is still contributing about twice as much to the planetary albedo. And through the rest of summer, the surface contribution just gets lower, while the atmospheric contribution is relatively consistent, so it's not as variable. And over different surface types, it also does not vary as much. So the atmosphere, and again, namely clouds, are having a damping effect on differences that we would otherwise be observing at the surface. And we can, again, see this with physical satellite imagery. So looking at the surface with relatively little cloud cover, you can pretty easily pick out where we have sea ice, where there's bare land, and where there's open ocean. But when there is cloud cover, those differences are harder to pick out. It's not impossible. We look down here, we can see where there's sea ice compared to land, but it's not as easy to pick out. And we can also see that from one year to another, while the surface might be quite different from a lot of sea ice to almost no sea ice, at the top of the atmosphere with clouds, those differences aren't nearly as striking. And so we find that clouds have a damping effect on the interannual variability of the planetary albedo. So starting in the upper right with the surface albedo, these are monthly averages over the full Arctic plotted against the average sea ice concentration, again for March through September. And as there's less sea ice, the surface albedo gets lower, and particularly in the summer months, as you probably expect, the surface albedo has a pretty strong linear relationship to sea ice concentration. But in these months, the sensitivity of the TOA albedo to changes in sea ice concentration is about half that of what we measure at the surface. Again, that's because the surface contribution, the magnitude of what's reflected at the surface that makes it out to space, is actually pretty close to zero over the full Arctic by the end of summer. And so again, it's the atmosphere that provides the bulk of the planetary albedo, and that is much less sensitive to changes in sea ice concentration and surface changes. And so that's why we get this damping effect of clouds seen from space. And we can use the same framework to evaluate how well climate models capture albedos and the partitioning of the planetary albedo. So shown here are again monthly averages for March through September based on CMIP6 historical forcing averaged over the years 2000 through 2014, which is the overlap of the historical forcing output with the series EBAF record. And previously, we were using a physical definition of the Arctic, but from here on out, we are just defining the Arctic as the area north of the Arctic Circle that's at about 66 degrees north and shown in this small map. So in these seasonal cycles, series EBAF or observations are this light blue line, and what we see that it falls within the spread of CMIP6 models. And so the full ensemble of CMIP6 is able to capture the mean state of the observations. So they capture the general decline of surface albedo and planetary albedo over these months. They also do a pretty good job of capturing the relative magnitudes of the atmosphere and surface contributions. So all models are showing that the atmosphere contributes more to the planetary albedo than the surface contribution. However, models start disagreeing when we look at how albedos change with sea ice area. So shown here are again monthly averages for planetary albedo and surface albedo over the full Arctic regressed against sea ice area, now over 1900 through 2014. Looking at the surface albedo first, both models agree that the surface albedo should decline with less sea ice, and particularly both models show strong linear relationships at the end of summer, which is good. But they don't agree at the top of the atmosphere. So EC Earth 3 on the right shows significant linear relationships to sea ice area during summer and into fall. However, BCC on the left does not. Its planetary albedo is relatively indifferent to changes in sea ice area at the surface. And so in these two models, their top of atmosphere energy balance will evolve differently as the Arctic changes and loses more sea ice into the future. We can look at the sensitivity of the TOA and surface albedos across the full CMIP6 ensemble. And we see that BCC is on the very low end of sensitivity, and EC Earth 3 models are at the upper end. And across these 18 models, the sensitivity of the surface albedo varies by about half. And while all models, oh, and this is just for 1 month in September. And while in September, all models show that the planetary albedo is less sensitive than the surface albedo, across these models, the magnitude of that sensitivity varies by about a factor of 5. And so there is not consensus among models of how much sea ice should impact the planetary albedo. And so from this first section of research, we've found that in observations, the atmosphere and clouds contribute the bulk of the TOA albedo and have a damping effect on its variability. And further, while CMIP6 models do a pretty good job of capturing the mean state of albedos, they do disagree on the response of the planetary albedo to changes in sea ice at the surface. Moving on, we're going to flip our thinking and start wondering how clouds impact shortwave absorption. And so remember that over the last few decades, we have seen pretty considerable declines in sea ice and snow cover, which we expect to lead to more shortwave absorption, certainly at the surface. But what those changes in shortwave absorption look like at the top of the atmosphere is a little more complicated and means that we have to consider clouds. And so to begin answering these questions, we have defined a new variable that we've called accumulated shortwave, which is equal to the total shortwave energy absorbed over the melt season, again, March through September. So to calculate accumulated shortwave for a given grid box ij, we first use monthly averages to calculate the net shortwave, and then multiply it by the number of seconds for that month. And so we get a measure of energy per area. And then we sum those monthly averages over March through September. And we've done this using series EBAF top of atmosphere fluxes over 2000 through 2019. And so we can do this with clear sky and all sky fluxes. And what we see is that without clouds, there is more shortwave absorption and accumulation as compared to all sky fluxes when clouds are present and there to reflect more shortwave. First, looking at the clear sky mean accumulated shortwave, the spatial patterns that we observe largely reflect the mean conditions at the surface. So in the lower left, we have snow cover fraction, and we can see the Greenland ice sheet sticks out. And in accumulated shortwave, we can also see that there are much lower values of accumulated shortwave. In sea ice concentration, we can pick out the North Atlantic that is warmer and has no sea ice on average, compared to the interior Arctic basin, where there's at least some sea ice for part of the melt season. And again, we can pretty clearly make out that transition of there's a lot more shortwave absorption over the Atlantic than the interior Arctic. But when we look at accumulated shortwave from all sky fluxes, over the entire Arctic, the mean values are reduced. So again, clouds are reflecting more shortwave. And the spatial patterns that are pretty clear without clouds are also smoothed over. And so the transition from North Atlantic to interior Arctic is a lot more gradual than without clouds. And I just wanted to show that with clouds, again, from visible satellite imagery, you can see that they complicate what you would otherwise see at the surface. And again, we've been interested in how the Arctic has been changing. And so we expect with lower sea ice, more shortwave absorption. And so shown here, we have trends in accumulated shortwave for clear sky and all sky. Stippling represents grid cells with statistically significant trends with 95% confidence. And we see that without clouds, there are regions with significant trends, even over this relatively short record. And the areas with the greatest magnitude of accumulated shortwave trends, so where we're getting the most change in shortwave absorption, largely relate to where we've seen the greatest sea ice loss in the interior Arctic. But when we look at trends from all sky accumulated shortwave, we don't see quite as many differences or as much change. So fewer grid cells from all sky fluxes are considered to be statistically significant. And if we look at the actual difference between trends with and without clouds, we see that clouds are reducing the magnitude of accumulated shortwave trends over the entire Arctic. And the greatest masking effect that clouds have is also where we've seen some of the greatest sea ice loss in the Barents and Kara Seas. And to go a step further, we are able to calculate the total shortwave energy over and into the full Arctic system. And so whereas before we were calculating accumulated shortwave into a single grid box ij, now we're going to convert our average net shortwave flux into shortwave energy by multiplying accumulated shortwave in a single grid cell by its area, and as well as multiplying by time, and then summing over the full Arctic, again shown here. And while previously I was showing accumulated shortwave only at the top of the atmosphere from clear sky and all sky fluxes, we're changing our perspective slightly. So we still are keeping all sky TOA accumulated shortwave, but now we will be comparing that to accumulated shortwave calculated at the surface with clear sky fluxes. And so this is just trying to tease out the difference of what we would otherwise be observing at the surface if we didn't have clouds, to what is really happening at the top of the atmosphere with clouds. So shown in this figure in the upper left, we have anomalies relative to 2001 through 2018 for clear sky in dark red and all sky in black. We also have plotted the linear trends over this time period, and this is a relatively short time period. It's just 18 years. However, the Arctic has been changing so rapidly. We have this new Arctic. And so we did wonder if these trends might be statistically significant. If they weren't significant, then how many years of observations would we expect to be able to say the trends had emerged? And of course, how do clouds impact those results? And so to answer these questions, we have used a combination of synthetic time series and trend detection based on work from Weatherhead et al. And Schaefer et al. And so because our observations are just 18 years, we also want to be able to measure if a trend takes longer than 18 years to emerge. And so we create synthetic time series that still represent the statistical properties of our observations. And the observations are shown here in black, and random noise that we've generated is shown in gray. And so these random values are based on the autocorrelation and variance from detrended anomalies. To this noise, we can add a linear trend shown in blue. And again, that's measured from our observational record. And so then the question becomes essentially, when does the signal rise above the noise? And to test when that occurs, we measure the trend after each additional year. So we measure it after 2 years, after 3 years, 4 years, 5 years, and onwards, as long as it takes. And this horizontal black line is the forced trend that we know exists in the time series. But initially, when we're only measuring over a few years, the trend is misleadingly large. But relatively quickly in this instance, the measured trend does approach the true value. And so after each measured trend, we test if it is statistically significant, which it is considered significant with 95% confidence when it's 2 times greater than its standard deviation, which depends on the variability, autocorrelation, and the length of the record used to make the measurement. So shown in this bottom left, we have that ratio of trend to standard deviation. And when that ratio becomes greater than 2, when it surpasses this threshold, we say that the trend has emerged. And the number of years for that to happen is called the time to emergence. And so one nice thing about creating your own synthetic time series is that you can create as many as you would like, and you can test each one. And so we have created synthetic ensembles of 300 members. And looking at all these different time series shown in blue, we can see that initially the trend varies from very negative to very positive, depending on the noise that's present in the time series, before they eventually converge to the true forced value. And again, we can test each of these time series, and we get a distribution of how long it takes a trend of this magnitude to rise above this noise. And so again, all time series have the same statistical properties, but sometimes a trend might emerge in fewer than 10 years, or it might take longer, up to 20 years. But from our 300 synthetic time series, we can find the average number of years we expect this trend to emerge in. And so we repeat this process for our accumulated shortwave at the surface from clear sky fluxes and top of the atmosphere with all sky fluxes. And at the surface, we find that the mean time to emergence is 12 years, which is within our observational record. And even if we just test if this linear trend is statistically significant using our criteria, we find that yes, it is. At the surface, the Arctic has been changing so rapidly that there is a measurable signal in absorbed shortwave. However, at the top of the atmosphere, the linear trend measured over the observational record is not statistically significant. And the expected time to emergence for that trend is 22 years, which is beyond our observational record. And so clouds are delaying the emergence of a signal in absorbed shortwave over the Arctic. And this is largely because the trend at the top of the atmosphere is less than half that of the trend observed at the surface. So again, we have this damping effect of clouds on changing shortwave over the Arctic. And returning to CMIP6, we can apply the same time to emergence framework to our 18 climate models. So for each model, we can create a synthetic time series, and we base the noise on variance and autocorrelation measured from the years 2001 through 2018, which is the same years that we have for our observations from series. We force those synthetic time series with trends measured over the 21st century from 2 future scenarios. So we use SSP 245, which is a middle of the road scenario. So there's moderate warming and moderate climate change mitigation over the 21st century. And we also use SSP 585, which is the business as usual scenario with no climate change mitigation. That's equivalent to RCP 8.5 from CMIP 5. And in these bar plots, we have the mean time to emergence plotted under both scenarios with observational values on the far right in black and gray. And across both future scenarios and actually both levels, the mean time to emergence varies by about a factor of 3 across the ensemble. And so with trends from both scenarios, some models are agreeing with observations that the signal at the surface for absorbed shortwave is measurable during the series record. And some models agree that the signal at the top of the atmosphere is not observable just yet. However, there are also models that disagree. So some models think that, or show that a accumulated shortwave trend at the top of the atmosphere should still be observable already in our observations, even with clouds. And other models disagree that the surface clear sky accumulated shortwave trend should be measurable yet either. And The differences in mean time to emergence across CMIP6 models is in large part explainable by their differences in sea ice decline over the 21st century. So shown here on the left are averages of sea ice area over March through September for each year, shown over the 21st century for historical forcing up through 2014, and under the business as usual scenario for the rest of the 21st century. And what we can see is that in some models, there's a relatively gradual loss of sea ice in the future, whereas other models have a pretty steep decline of sea ice loss with climate change. And in those models with the greatest loss of sea ice, so the most negative sea ice area trends, they also have the smallest mean time to emergence for accumulated shortwave trends. And so this makes sense in that when you lose more sea ice and your surface albedo lowers, you'll have greater shortwave absorption trends and larger trends emerge faster. And so you can see, again, this large spread across climate models of the middle of the road scenario typically has lower sea ice area trends and longer time to emergence as compared to the business as usual in the orange and red. And we can see that observations are in the middle, maybe at the upper end of the middle for both sea ice loss and time to emergence. But remember that in observations, we found that delaying effect of clouds on the detectability of trends. And so we look at observations, we see that the surface clear sky time to emergence is less than at the top of the atmosphere with clouds. And in the middle of the road scenario up top in blue, half of the models agree with observations. And so half of the models are showing that clouds delay the detectability of shortwave absorption trends over the Arctic. So in particular, we have BCC and NESM3, some other models in the middle that show this delaying effect. However, the flip side of that is half of the models don't agree with observations. And so some of the models are showing clouds have no measurable impact on trend detection of accumulated shortwave. And some models even show that clouds decrease the time to emergence. So the all sky trend at the top of the atmosphere is more readily detectable than at the surface without clouds. Under the business as usual scenario below, things kind of worsen. So fewer models agree with observations that clouds increase the time to emergence, and more models are showing that clouds either have no impact or decrease the time to emergence. And even in climate models that still show clouds have a delaying effect, the amount that clouds delay or increase the time to emergence also reduces. So we can see there's a bigger difference in BCC in SSP 245 than in business as usual SSP 585. And we believe that this is at least in part due to changes in cloud cover and shortwave reflectivity in the atmosphere over the 21st century. So in some models, clouds have increasing cloud cover over the Arctic, so they have positive cloud fraction trends. Other models show decreases in cloud fraction over the 21st century. And those seem related to the ratio of time to emergence for clear sky at the surface to all sky at the top of the atmosphere. And so a ratio greater than 1 means that clouds decrease time to emergence, whereas a ratio less than 1 means that clouds increase TTE. And again, that's what we saw in observations. And so in models where they are gaining cloud cover over the 21st century, we consider that more cloud cover could increase more shortwave at the atmosphere and have some sort of partial compensation for the loss of sea ice at the surface, as compared to models where not only are they losing sea ice, they're also losing clouds that are highly reflective in the atmosphere. And we can more directly quantify the change in shortwave reflectivity by the atmosphere by defining one last variable. And so if you remember back 30 or so minutes when we discussed the planetary albedo as being a contribution or the sum of contributions from the atmosphere and the surface, we can look at how that changes over the 21st century. However, that analysis used monthly values that are rather difficult to relate to accumulated shortwave since it's a summed value over a full melt season. And so we calculate the total shortwave energy reflected by the atmosphere in a similar manner to accumulated shortwave of converting a flux to an energy and then summing over the Arctic and the melt season. But instead of the net shortwave, like accumulated shortwave, we measure the shortwave that is reflected by the atmosphere. And so when we look at how this variable changes over the 21st century in climate models, most models predict that the atmosphere reflects less shortwave into the future. The one model that has a slightly positive trend is also the model that shows the greatest masking effect of clouds on the detectability of shortwave trends. So that's BCC. And generally, as models have more negative trends in atmospheric shortwave reflection, so as the atmosphere reflects less shortwave clouds, the all-sky accumulated shortwave trend tends to become more detectable, and so there's less of a masking effect by clouds. And changes in cloud cover and changes in atmospheric reflectivity are, of course, not independent. And so we do see that generally in models that are gaining cloud cover in the future, also their atmosphere either is increasing slightly in reflectivity or it's just not growing as less reflective as compared to models that have less cloud cover over the 21st century and show the greatest reduction in shortwave that's reflected by the atmosphere. And so future work could further explore these relationships. In this work, we kind of stopped looking at cloud properties after cloud fraction, but of course, other properties of clouds are also important to their reflectivity. So investigating cloud phase and cloud water path could also help further explain differences in time to emergence, as well as looking at various cloud feedbacks that might be present in climate models. It could also prove interesting to try and relate this accumulated shortwave and time to emergence framework to other climate model properties. So equilibrium climate sensitivity, which is the expected warming due to a doubling of CO2, is a pretty common metric used to evaluate climate models, and trying to relate our time to emergence to ECS could prove an interesting way to, again, try and use observations to assess climate models and how they predict changes in a warming climate. And so in conclusion, I hope that I've convinced everyone here that clouds are important for shortwave energy in the Arctic. And so in particular, our results have shown that the atmosphere, and again, namely clouds, contribute about 2 times more, at least, to the planetary albedo than the surface does. And that clouds have a damping effect on the sensitivity of the planetary albedo to changes in surface cover. And further, that clouds reduce the magnitude of accumulated shortwave that's absorbed over the Arctic at the top of the atmosphere and dampen the trends that we would otherwise see. And that while we did find a statistically significant trend at the surface without clouds, clouds have masked that trend from being from emerging at the top of the atmosphere. And when we compare to CMIP6, we find that models have a fair amount of spread and disagreement on how clouds impact both the top of the atmosphere and the emergence of accumulated shortwave trends. And so with that, I now get to thank everyone for everything from over the past 5 years. And so obviously first, I would like to thank Tristan for being my advisor and for giving me the chance to do this research and basically make all of this possible. I also want to thank the rest of my PhD committee for giving helpful feedback on this work throughout the years, and in particular to my committee members who are not faculty now or were not when they joined. I extra appreciate your time. As a grad student here, I've also been lucky enough to be part of a great and large research group. And so my fellow grad students and the associated research scientists in the Lekway group have been so helpful throughout the years, both in terms of research and general well-being. And speaking of which, our Polar Coffee little subgroup that's been meeting every week was great before the pandemic and has been indispensable during this time of working from home. The general AOS community, I'd also like to thank both my fellow grad students for help throughout the years, the staff who help run this place, and of course, the various professors who have helped me learn about the atmosphere and go from someone who was interested in the climate to someone who actually understands some of the science behind it. And I have also been fortunate to be supported by family and friends outside of AOS. So my sister, who I think is listening, has been an incredible role model. She is a scientist and a brilliant scientist in her own right. And she has helped show me how to be a scientist and navigate graduate school. And last but not least, I need to thank my husband who has loved and supported me through all the highs and lows of this year, or these 5 years. And so with that, I will take any questions.
All right, thank you very much, Anne. I'm kind of waiting for the virtual applause here from a lot of different people, but if anybody has any questions, feel free to raise your hand or type something in the chat, but I think we can basically all just read out questions if we have them. I think Brad is first.
Yeah. So first of all, that time to emergence analysis is really, really elegant. That's very well done. And any questions that I was anticipating during your discussion were answered in the discussion. So my compliments to that analysis.
Thank you. That's really nice
And
to hear.
it does seem to be a very powerful tool for looking at the CMEP models. You showed in the anomaly time series, there seems to be a pretty strong biennial oscillation in both the surface and the top of atmosphere, more so in the surface. And it almost looks like it's amplifying. Is there any, I know it's probably just speculation, but I'm wondering whether there's any, is that something that you could test its significance as well?
So, how do I see if I can share just the PowerPoint? Go back to, so you're talking about how it's getting more variable.
That one right there. Yeah, it just almost looks like
yeah,
it's amplifying.
So yeah, so I guess you could just test if the variability has increased in the second half of the observations compared to the first half. In looking at the autocorrelations, they are not statistically significant, but I think that's more a function of the fact that it's a short observational record. And with fewer years, you need to have pretty large correlations for them to be significant. But yeah, it does look like the Arctic is having some more extremes in more recent years.
Thank you.
Okay, Till.
Hi, can you hear me?
Yes.
Hi. Great talk. Really enjoyed it. Thank you so much. I had a more general question about the clouds in the impacts of the clouds in the models, which was, do you have any insight into how much of the differences between the models is due to different cloud physics versus, or do they all use similar cloud physics and these differences appear due to other differences in the climate representation?
So I would guess that a large part is due to different representations of the clouds. So in all models, the trend of accumulated shortwave at the surface with clear sky fluxes, it's always greater than at the top of the atmosphere without clouds. So in all models, there is that damping effect. And so I think it's really in part the mean state of the clouds and the cloud physics of how they influence the magnitude of that damping effect and how much they mask the surface. And so I've heard from some people of a specific model does not do a great job of masking the surface. It doesn't have as much reflectivity. And so I have not gone into all 18 models to figure that out. But my guess and kind of the thought behind this work is that it would be motivation for looking at the reflectivity and masking effect of clouds.
So it's not that they all use exactly the same cloud module and the differences are due to...
No, I'm pretty sure that there are different atmospheric models used in different models. And at the very least, like I show results from CSM2 with CAM6 and WACM, which are two different atmospheric modules.
Great, awesome, thank you.
You're welcome.
Okay, are there any other questions while we have the full audience here? Okay, I'm not seeing any other hands up and we are getting pretty close to the hour. So if there's no other questions, I'll invite everybody to once again give Anna a round of applause here. And then what we'll do is for the committee members themselves, I'll say we'll drop off this call and we'll go on to, I think, a separate Zoom link that Ann set up for the post committee meeting in say 4 or 5 minutes here. So congratulations, Ann, very nice.